Assalamu alaikum, guys. In continuation of our previous lecture, Tripoli 4403, today's topic is double sideband modulation. So our topic is double modulation. DSB. So let us, we have seen in our previous lecture that when we modulate a signal, then our modulation efficiency actually in M modulation, amplitude modulation, the efficiency is very less due to the transmission of the carrier. So if we do not transmit the carrier, if we only transmit the modulated version of the sidebands, not the modulated version of the carrier, then we can save energy or we can increase the efficiency. So in that case, we will only transmit a double sideband, not the modulated carrier will be transmitted. Okay, so let us assume this transmitted carrier, transmitted modulated signal is xt, which can be written as AC mt cos 2 pi fct. Here fc is the carrier frequency. This is actually our carrier frequency, and mt is the message. So mt is the message signal, and there is no pure carrier here. So there is no pure carrier here, which is unlike to the previous, when an AM modulation, the carrier, a pure carrier was there in the modulated signal. So this is also called as a double sideband suppressed carrier. So this is called, this portion is the, this is the suppressed carrier. Suppressed carrier. Okay. So the message signal, if we draw the message signal, the spectrum of the message signal would look like this, right? In frequency domain, MF. In the empty, the message signal empty in frequency domain, it's look like this. Okay, so if we rewrite this equation, then we can write mt into AC cos 2 pi fct, right? So this is our modulated serial or DSB signal, right? Modulated DSB signal. If we do the Fourier transform, we will have xt become xf, then mt becomes mf. Now we already know that multiplication becomes convolution in frequency domain. Okay, so this portion becomes AC by 2 del f minus fc. Okay, f minus fc plus AC by 2 del f plus fc. So what we have here is, whenever we do our Fourier transform, so we can write, so this MF will be convolute to this component and as well as this component. So we can write AC by 2, this MF becomes MF F minus FC. We can write actually small letter also. F minus FC. It's okay. F plus FC. No problem. F minus FC. Because conventionally, previously we also write probably F minus FC. This is okay, no problem. So AC by 2M F plus FC. So this is actually the complete spectrum of the DSB. This is the spectrum of double side band suppress carrier. So from here we can see that when MF, the MF is convolved with del F minus FC is MF minus FC. That means MF is shifted to FC and MF convolved with del F plus FC is MF which shifted to minus FC. So that's how we got these two components. We actually have seen this example earlier, so I'm not going to detail of this one. Okay, so if we draw this spectrum here, how it look like, it will be so this is our actually center. So here will be FC. So this is actually FC. This is minus FC. If this is the case, then we have one component here and we have another component here. So this will be FC plus FM and this will be FC minus FM. This portion here, actually, this is the center. This is the center. And this frequency will be F minus FC plus FM. This will be minus FC minus FM. Okay, so this signal, this will be AC by 2 MF minus FC, the first component, this part, and this will be AC by 2 MF plus FC, the second component. So which is this is here and this one is here. So this is the complete spectrum of the, so this is actually spectrum of double sideband suppressed carrier signal. Now, so imagine we modulate the signal by DSB, then we are transmitting. So how to detect in the receiver? It is done by the demodulation. So how this demodulation is done? So demodulation of double sideband suppressed carrier. So demodulation can be carried out by multiplying with a coherently generated carrier at the receiver. So what we can write that demodulation can be done by multiplying the received signal, which is actually this one, like this one, this signal. So if once we receive this signal, we multiply with a carrier of this same signal. So we say this is actually coherently generated. Coherently generated carrier, which is actually nothing but the cos 2 pi fct. This carrier at the receiver, of course, at the receiver. Here, two what is very coherently generated, and this is the carrier. Okay, so once we receive this signal, we multiply it, or actually in equation, this signal. Once we receive this signal, we generate this signal, or we multiply this signal with our carrier, this one, at the receiver, and this carrier is generated coherently. So this, for the sake of this lecture, just remember this terminology. We'll explain it in later lecture. Okay, so how it works. So the receive signal RT, so the receive signal receive signal RT, for example, we have the transmitted modulated signal XT, right? So we actually multiply this signal with a carrier cos 2 pi fct, this one. Okay, so we already know what is XT. XT is nothing by SCMT cos 2 pi fct multiplied by cos 2 pi fct. Okay, so we say there are two cos term here, which is the CMT cos square, right? Cos square, so it becomes cos square 2 pi fct. So we can actually put it in a formula. So 2 like CMT, this is unchanged. So assume this term is 2 cos square theta. So 2 cos square theta becomes 1 plus cos twice theta, which is actually becomes 4 pi fct. But there is no 2, so we divide it by 2, right? We know 2 cos square theta is nothing but 1 plus cos twice theta. That's actually our formula, right? So this is how we have the solution. Now just make it like this: half AC MT plus half of AC MT cos 4 pi fct. Here, this term, this is nothing but the baseband signal, and this term is actually our the modulated frequency. So this is the baseband. So this is the baseband, and this signal is, you see, it was supposed to be 2 pi fc. Fc would be twice fc, right? T means actually it's centered at twice fc. So we know this is actually centered at twice fc. Okay, so let us see how this signal will be look like in Fourier transform. So this is actually our R in T. Okay, so if we do the Fourier transform of this part, this signal, Fourier transform, what will happen? What will happen if we do the Fourier transform? The half of AC and MT, they remains M. Half of AC, MT becomes MF. So this is actually capital M F plus following the previous here you see this is a dot, means actually this is a multiplication, which becomes the convolution of MF. So it will be nothing but AC, I'm not deriving this because we derive it many times. So AC by 4, there will be half extra. So this half will be multiplied with this half. So it becomes AC by 4. So MF, so MF will be convolute to the del F minus twice, F minus twice FC plus del F plus twice FC, because our center curve is twice FC. We know it from here, right? Okay, so if the convolution of MF with this one, the result will be, we know, we already solved it many times. So it will be nothing but half of ACMF plus AC by 4, and MF will be convolution with a del F minus twice, means MF will be shifted to twice FC. So MF will be, so MF minus twice FC plus AC by 4. This MF F plus twice FC, it is shifted to twice FC. That's actually we are saying here. So if I draw this, picture, if I draw this in frequency domain, so this is the frequency signal. If I draw it, okay, if I draw it, drawing was not nice. Okay, so if I draw it, then I can find, okay, imagine this is actually our center, and this will be twice FC. So twice FC, one center will be there, the image copy will be here. Means so this will be actually our one of the, so this will be the another one, and for this one, this will be the another one. Here this is actually twice FC. This is actually minus twice FC. So this portion will be FC plus twice FC. So okay, now, so okay, so this portion is the baseband. This is the baseband. This portion is the baseband, which is actually this one, where it will be FM2 minus FM, and this signal will be what? Half. This is the half AC MF, right? And this is what? This is the first portion of the signal, right? So this is AC by 4 M F minus twice FC, and this portion will be the second one, which is actually AC by 4 M F plus twice FC. Here we see whenever we receive the coherent remodulation, then we receive the sidebands, like this sidebands, this one and this one, with a baseband. Now, by using a low pass filter, we can kill the baseband, right? So if we use a low pass filter here, if we use a low pass filter, whose frequency will be W2 minus W. So this is actually a low pass filter at the receiver. So at the receiver, if you use a low pass filter with a bandwidth of twice W, so this is actually a bandwidth of twice W, then we can kill this baseband and only the sideband. Side band at twice Fc and minus twice Fc, which actually this one and this one, they can only be received. Now here the width of this low pass filter W has to be like chosen properly, so that only the low pass, only the baseband is suppressed. Okay, so what we can say that choose. So we can say that choose a low pass filter with suitable suitable bandwidth AC, so that AC by 2 MT means actually the baseband signal can be separated from AC by 2 cos 4 pi FCT. So this is actually about the baseband. So this is our baseband, and actually this is actually our sidebands. So choose a low pass filter with a suitable bandwidth so that the baseband can be separated from the sidebands, because we do not need baseband. Okay, so the cutoff frequency, so we can write the cutoff frequency of the low pass filter. So we can say F cutoff frequency of low pass filter, it should be much higher than Fm, which is actually here. You see the this here, and this one is much higher than the Fm, so that there is a sufficient distance between the separation, like separation, because there is enough separation. There's enough separation. So choose this value such that that this is actually greater than or equal to twice of Fc minus Fm. So choose this cutoff frequency of the low pass filter such that it is greater than the Fm, much higher than the Fm, which is actually here in this figure, and it should also be lower than this one, which is actually this one. Like this bandwidth cutoff frequency is actually higher than this one, but it's actually lower than this one. That actually is saying to, so which actually realizable, because we know that Fm, the frequency of the message signal, is much lower than the Fc, the carrier frequency. So we can say that, okay, so twice Fm also much than twice Fc, which is actually ultimately give us Fm is much lower than the twice Fc minus Fm, which actually this condition. So this is realizable. So we know that, okay, this is realize, means the condition we have, the cutoff frequency of the low pass filter is actually a practical one. Okay, so this is actually the condition that a double sideband suppressed carrier in the demodulation should follow. So here ends our lecture. Assalamu alaikum.